As usual, waiting for Twitch to catch up. There we go. Okay. Hello, everyone. Welcome back to the stream. So, last week was mostly about catching up, starting the project again after a long break. Last week, as a result, we've mostly been doing cleanups, adding tests, cleaning up some old to dos in the code, trying to fix up some errors in the documentation, fixing some basic bugs, that kind of stuff. And one big point I was thinking about last week was what do we tackle next? Now that the analysis is kind of done, or at least a big batch of it is done, the question is what do we start working on? One thing I was thinking of is now we have the output of the analysis, which is something that we will want to persist because we will want to cache it. That will probably require having some kind of file format, although we can probably use a library that already exists, but maybe we want to work on that. Maybe we want to write a visualizer for that file format. Maybe we want to start working on other parts, like starting right on the compiler architecture, compiler options, and that kind of stuff. What I've decided instead is to start this week working on the next phase of the compiler, the lowering into the IR. The reason why is I think the sooner we are able to have at least something for each of the phases, the sooner we can start doing end-to-end tests, the sooner we can start iterating on something that has a full pipeline, basically. So today we're gonna start working on the IR, which means we need to start defining what the IR is going to be like, and we need to start working on the transformation from the resolved AST into the IR. For people who are interested, I have linked that on the documentation on GitHub. I will be following the algorithm outlined in this research paper from 2013, a simple and efficient construction of static single assignment form from the AST, which has a big upside compared to previous algorithms that tend to work on a existing control flow, control flow graph already pre-established. This one can work directly from an IR, but there is one subtlety is I am planning to make a change to the algorithm that is outlined here. This one uses phi functions for variables that have variables registers in LLVM IR lingo that have different values depending on which block we're coming from. I am planning to use something that was introduced, I think, after this research paper came out called block arguments. So I'm going to have to adapt this research paper on the fly when we start actually implementing the transformation. Although this evening is probably going to start with trying to define the IR in the first place. And there are so many subtleties here. I've tried to think ahead of time about some of the design decisions we're going to face, but there's just a lot of things where there's no other way to know exactly how to do this than just to try. So, yeah, let's go. Put this back here. And come back here. And open this. As you can see, I don't have much yet. The IR was basically an empty file, a placeholder. There's one thing I wanted to quickly check, actually, which I think is at the moment in the analysis. What is my definition of a symbol? I have here a symbol cache. Name symbol. And what is a symbol? Where's that defined? Oh, is it already in the representation? It is. Okay. So I have two kind of symbols, functions and constant. Okay. Not sure why I've called this symbol. We'll see about that. Okay, anyway. So our IR will be something that lists basically a set of instructions for each function. And I think I will represent it as kind of a graph of blocks where each function will have like a start node and will execute the functions and might jump to another node at the end. There's a few things I'm not sure. Do I include a return node for each function, or does every block deal with the possibility of return individually? There's a few things I have not decided on. The idea, however, is that each block will, in a sense, be um, basically labels within the LLVMAR when we do the actual export to the LLVMAR, which is a side project I want to do at some point, but not something we're going to be doing this evening. So, the main thing of the static single assignment is each operation will assign something to a new unique register that never gets overridden. Then we'll do register again in the sense of the LLVM When we actually do code generation, we will assign a place on the stack to each of those registers, and we will reuse places rather than introduce more stuff on the stack as we go. Um, but as a result, we're going to decompose all of the possible things that we have found in the AST into a sequence of very, very basic instructions. Most of them will be either of the form of assignment or branching, basically. The one thing I'm not sure about is how I will deal with functions that do not return a value, like void functions. Because a function call is an expression. Expressions tend to be assigned to a register as a result. As part of the construction of the IR, do I assign the result to a register, or do I make the function call instruction have a maybe register, which creates some inconsistencies between function calls that do not return a value and functions calls that do? Some questions there. I think I might make simply two different instructions, void function call and non-void function call. That way, in the case where we have a non-void function call, we know we have a value that needs to be taken into account, will be on the stack, even if it ends up being ignored, versus a void function call where we know there's nothing on the stack. So, let's do this. What kind of operations will we need? And I'm gonna actually open the AST here, because a lot of the things we're going to do are going to be based on the kind of expressions we support. If I look at the statements, actually, if I start with statements, if will be represented as a the if will be represented as a simple jump, like a jump if non-zero, and then like maybe like a double, maybe a special jump instructions for if to always jump to another block. While will be that kind of stuff as well. For yeah, so all of those will be handled like this. Let, I suppose, will just be a normal case of assignment, like do an operation basically, which is what we were gonna already planning to do. So I guess continue are and break are also jumps. Which will just jump back to a given block. And then we have expressions, and expressions are the main thing of this. So what kind of instructions do we have? We have, let me think about this. Because we're going to have the basic. We're going to have an add instruction that will take a target register and then two other registers. We're going to have a subtract, which saying likewise we would have a target and two source registers. Multiply, divide, which are those basic ones. Let's have a look as well on what is, okay, this is going to be a bit hard to read on stream, I think. I'm curious about the bytecode, which is the list of, okay, I do have greater but not less than. But I think for the purpose of the IR, we can probably represent the different kinds of operations, and we'll translate that into bytecode later on. Okay. So modulo, of course. Or maybe... No, I think this is fine. We will have equality. Do I want to call that equality? Because I've named them more as verb: add, subtract, multiply, divide. Modulo isn't a verb. I could look at what LLVM names them, or maybe compare equality. Compare difference. Compare greater. Let me think about this. There's like, what instructions do we need and how do we name them? I think I'm gonna use the 2-letter abbreviation. Equal, not equal, greater than, greater or equal, less than, less or equal. Okay. Do I need to have, in my AST, I do a distinction between a Boolean negation and a normal and an int negation. Does that make sense here? I think it makes sense to keep them different because those will be translated to two different things. Those will be translated into two different things when it's time to do code generation, because one will be 1 minus the value and the other will be minus the value, 0 minus the value. So yes, let's keep both. We'll have int negate int register negate b. However, we might not need to keep boolean and boolean or. Those can be add and multiply, as long as booleans are properly represented by 0 and 1, basically. As values, this is fine. So we can replace them by simple multiply and add. Although, I was going to say maybe we want to actually not do that to avoid having booleans and then not something that is not 0 or 1. Would there be any issue with that? Yes, the Boolean negation will be complicated to do if we don't have the guarantee that it's 0 or 1. Well, difficult to do. More annoying to do. So maybe actually we need to keep them as separate things so that at code generation time, we know we're generating something different. And we still are able to do that. Okay, so we still have end. Or I need to keep the cast actually, which is peculiar, but some casts will need to insert code at code generation because some casts might fail at runtime, like cast from int to an enum, for instance. If I have an enum color with like three possible values, red, green, blue, that has values like are represented by the ints 0, 1, 2, trying to cast 3 as a color will fail at runtime, which means a cast is not just a type checking operation, it needs to have code inserted at runtime. So cast will have to stay as an instruction in the AR, and it will be something that has a target register, a source register, and some type information that I don't know what's going to be there yet. We'll have to figure that out. Range, I'm not going to do that yet. Assignment is not something like all of those will be translated into one of the above. So that's, I think, and I guess there are literal values. There's just set, which sets a value to, which I guess I'm gonna call a push in a sense, or an assign. Register, which is the initialization of a given register to a given value, and that will take. What will it take? Do I need to have one per basic type? Or can I have some kind of now I think I'll need to have one such instruction in my IR per kind of value there is. Or do I? Yeah, because I don't have a type that encapsulates this kind of possibility. So I will need assign, which will take an int. I'm not going to do strings yet. And there's a few more things. I'm going to need instructions for structs. I'm going to need I'm going to need an instruction for getting a given field of a struct and and I'm going to need an instruction for updating. I'm going to need an instruction for updating a field of a struct, which is going to be, how do I call those? Retrieve, assign. No, I don't like this. Get, set. Yeah. Get field. Target register. Source register. Index of the field that I need. And maybe I'll need to put some type information there for the code generation. Or can I remove all type information at this point? Because some of the code, given that I'm going to have some dynamically sized type, I'm going to need to have type information as part of the code generation. So I think type information will need to be preserved as part of this. So maybe register will carry the type information. Or I will add it elsewhere at some point. I Don't know. So here, this is going to take the target register, the source register, the index, and the new value. This, of course, at code generation time will override the previous value, but in our single static assignment, we cannot do that. Okay. I think that should cover everything, except I think references. But references are peculiar. They're not exactly. References are peculiar. How do I want to do this? They are a peculiarity of function calls, where basically a function call will return not just one value, but a tuple of values of like it will change the stack to contain different values and not just like it will modify things in place. But in practice, I think in my model, it will be that this function leaves the stack differently than it found it, basically. Do I want to keep this abstraction as part of the IR, or do I want to model functions that have references as something that return multiple values? I think I will want to do the latter, since the way function returns are going to be implemented, I'm going to have to also like know where to find on the stack the return address. Since I only have a stack and no registers and nothing like this, I think I will need to know that. Okay. So that's going to be the tricky thing then. It's a function call will have a list of registers associated with it, which is the result of all of the places of all of the values which correspond to hmm that's tricky. Okay, I'm not going to resolve the problem of references right now. I'll think about it when I get to that. I guess now there is, and I guess then the problem of void function calls becomes moot because void function calls might still return values on the stack, which would be the changed values of arguments that have been given by reference. So I suppose that invoke will have a symbol or something like this there, which is the thing that we need to go to. That's not a branching thing because execution comes back after it. And it will have two things. It will have a list of register, which is where we assign the results, the names we put to the results of that function call. And there will be a list of register, which is the arguments we're giving to that function call. And I think, no, that's not all. We need also a struct creation function, which takes several registers and returns a new one that contains all of the fields. Combine, I suppose. And there's always here as well the question of how do we carry the type information? That is something that I don't know yet. We will need that because I can't transform the get field set field into operations that are like type independent purely by doing indexing because some types will have dynamic sizes, which means getting a given field might require doing some shenanigans to know exactly how many times we have to roll the stack to get the value we need. Okay. So that is a first draft definitely not good enough of the kind of instructions we have. And most of those are the kind that update, like create registers. And I'll actually do this to make it very clear which ones are the targets of a assignment and so on. Now we need some branching ones. We need an unconditional branch, which I'm gonna call go-to. We are gonna need a jump if, like a jump if zero non-zero, basically, that does an if kind of thing. Which will take to label and a register. Based on the value of that register, where do we go? And do I need anything else? Do I need anything else? The idea of this is basically that there is never a jump in the middle of a block. A block, or there's not like a jump if and then the block continues. Those instructions always end a block, basically. But there's also the argument of, as a result, do I want to not represent them as normal instructions and instead have a block contain a special case of the last instruction is one such jump, basically, because otherwise there's nothing for it to do, and that's weird. Hmm. Yeah, maybe those, for the sake of, I want to do something like this. I want to have something separate, which is, how do we terminate a block? How does a block end? And that is with a jump, unconditional, a branch, which takes two different labels and a register and branches on that thing not being zero, basically. And we have, I guess, return is just jump to a special block, which is the end block. Okay. So that means that a function, or maybe let's start with block. A block is a series of instruction followed by I might not need that actually. Maybe it's enough to do. No, I think I want to name them just for convenience. So a block will be a list of instructions. List might be a terrible type for this. Maybe we'll want to make it a vector or something like this. And a terminator, which will be the jump instruction at the end. So where do we go from here? And then I suppose a function in our IR will be something that has a starting block something that keeps track of all of its labels. And then I still need to keep track, since the block do not point as a graph. There is a level of indirection. Like those terminators are not like don't contain blocks here, because that would create. Okay, do I want to do that? I could do the thing where I create a full cyclic graph of blocks pointing to other blocks because they contain a terminator that points to another block, which requires doing some monad fix nonsense to basically do tying the knot shenanigans to be able to recover laziness in a monadic context, that kind of fun stuff. Or I can use the label as a indirection, and I think I'm just gonna do that. I think that's a lot easier. Although it means adding lookups in hash maps, it is slower and introduce error paths. It makes the code a lot simpler overall, I think. So I think for flexibility, even though it makes the code a tiny bit more brittle in some ways, I think we're gonna do a hash map from label to block, which means the label is no longer required. That's the set of the keys of the hash map. And what else do we need? We'll probably need the arguments, the return type, and so on. Which I might represent with registers if registers are typed. Yeah, I think I will carry the type information in the registers. I think that's the easiest. So do I need to carry a list of the registers? No, but I can do the arguments. It's just going to be a list of registers. And the return information, which is going to be a list of register. And lists because I will represent functions that take references to values as returning the new values for the things that they were getting a reference to, and the original return value of the function, if any. Okay. Now we just need to decide what a register is. In the context of our IR. And a register will be something that has. It needs to be unique throughout the function, but a monotonically increasing int should be enough. That word is hard to pronounce. So maybe just a register index is enough. And I will want a thing to carry type information because I will need to know, because since not all types size are known at this point, for code generation, I will need to have the type information, although type checking is already done. So I will need to have that information. I don't know what a type is yet at that point. And I guess type I can define, because there's only a few primitive types and then structs, and that's about it, and arrays, which I don't have yet. But as a result, a type will always be a finite list of things. A register will always be either an int, a boolean, a character. So all the primitive types, basically. Do I want to do it that way? I will need to have a list at some point anyway. There will be string type at some point, an array type, and I think the string type will just be an array type anyway, which are the dynamically sized ones, which is going to be very annoying, and a struct type, which is just a list of type. Which, since we're dealing with something that is purely stack-based, a struct that contains an int, a character, and a boolean will be those three things on top of the stack, basically. Okay. And I guess I need an enum, and I think an int is enough since enums will be represented as int values from 0 to something, and that int is the only the reason why I care about it's not an int, it is an enum, is because I will need to do bound checking for casts. I guess in debug mode, maybe in runtime mode, those are not required, but okay. I think that's enough to get started in our representation of the of a function of the AR. No, there's one thing that's missing. The block arguments are actually missing. I will need the registers as arguments as well. I will need the block arguments, which are going to be a list of register. Okay. And I guess I can make every block end with a terminator and have a special label which will not be part of this, which will be the return label, which will have a special name or something like this. That when I do code generation, I will introduce a special label for the return. Or maybe I make this thing an either block or return or something like this. Because maybe some labels are special. Actually, this is probably a label of the block. Or actually, it is a block. There is no need to have a label for the first thing. The very first thing in the function is a block that doesn't have an associated label. Maybe that makes more sense. Or maybe the terminator of a block can also be a return. And rather than saying that block doesn't, like, goes to a special return label, it just actually returns altogether. And it must return a maybe register, I suppose. Because some functions will not return a value and therefore will have nothing to put on the stack. Because yeah, jump, branch are within labels within the thing. Invoke another function is part of the instructions. There's no actual go to stop the execution, set jump, long jump, or anything like this. So maybe this is how we do this. Okay. I still don't know how I'm gonna represent taking references to something for the sake. I might not even need to do that. Maybe with the principle of like single static assignment, I'm just giving a register and getting a register back. Maybe it's just, yeah, maybe I don't actually care about references given the way they are used in this made up language of ours. Okay. Is there anything I'm using here that I haven't defined? Yes, I have not defined symbol. But symbol already exists, so I don't need to define it. Is it symbols plural? No, singular. I haven't been very consistent on that. Okay. Oh, I suppose I no longer need the negate that is because I will know the type and how to implement it based on the type information of the register. That being said, if I do that, then I will have to check that the type I have is one of the correct types and I will introduce error paths. I mean, otherwise I can, yeah, but I will need to do that anyway, so maybe I can just do a negate and I don't have, yeah, maybe it's do that. That being said, I'm not sure I like the idea of, yeah, let's do it that way for now. We will see. I think I would like to have like one instruction per kind of operation, per typed kind of operation, rather than having something that means different things based on the type. The type information is only there for size information. At this point, we should have basic instructions for everything, I think. Okay. And I think keeping the invoke like this with a symbol might make sense in the sense of like constants. This is either constant or functions, but some constants will not be inlineable. For instance, every constant that's like a string or something that construct a complicated struct, maybe those I will not want to inline, and instead I will want to make as basically a function call of some kind. So maybe those will actually be implemented as an invoke. Okay, so that should be everything, I think. The only thing I don't like is having the maybe register here, which means that like I will have to check further down the line that if a function returns something, it does have a register there. But I guess I can assume that the code that this will always be correct as part of the lowering, and therefore that the code generation can assume that this is correct and not have to double check. Okay. So now is the part where we start implementing this. So one thing that is very important is we're not starting with a pre-made control flow graph. So the thing we need to know is whether we have all of the information about parent graphs. And do we know that a block is sealed before we actually start iterating through its instructions? I think we do, because there is no arbitrary go-to in this language, which means the only places where we will have something that requires going back and therefore dealing with potentially non-sealed blocks will be while loops and for loops, basically. Loops in general. So we might be able to like do something a tiny bit simpler than what they do here by knowing that the cases of cyclic things in our control flow graph are extremely restricted. Okay. There's a lot of things where like I'm not sure exactly how we're gonna do this, but I guess there's no other way than to try and see what works and what doesn't. So let's go. So the lowering thing, will that be in isolation or like can I write a lower function? Not lower, but like maybe lower to IR. Does it take a function in isolation and then does it take a function in isolation and then returns a function out of this? Or do I take this whole thing what is again a symbol cache? And the symbol contains the definition, if I'm not mistaken, right? Here's the function info. Okay. Ah, but this does not contain type information. So I will need the definition cache for type information. Because I will need to bundle the types. There's also the question of like, how do I name the types I ever encounter in the AR when I do the LLVM IR generation? Maybe I need to give a unique name to structs just for things to be that, or I don't, and I just maybe I don't, and I just generate a name based on their shape and maintain a cache. Maybe that's the best thing to do. The generation of LVMIR is not a thing we're going to do this evening anyway. But I think we will need to have, yeah, at the very least, the definition cache and the symbol cache are going to be required for everything we do. Because we need to be able to do type lookup to generate type information for a to generate type information for the registers. We need the symbol cache to check. Actually, we might not need the symbol cache, come to think of it. Because the only place where we need symbols in the IR is for the invoke. But I think, unless I'm mistaken, my call expression contains a path info. No, we will need to translate that into a symbol, I think. So we will need to check for the existence of that symbol. Oh, and there is, since theoretically we handle function pointers, there might be a few places where I don't invoke a symbol, I invoke a register. I need to handle that. Okay. Okay. Maybe that's not what I want. Maybe this is not the right... Yeah, maybe I just want the name of the thing I'm invoking. Okay, so that means here there is invoke n, where I invoke a given name, and there is invoke r, where instead I look at the function call in a register. Okay? And there's no longer any symbol. I point to a unique name, which is something that uniquely identifies something in the program. Okay. Which will be all of the outside references. Do I still need, as a result, when I do my lowering, do I still need the symbol cache? I don't. I think I only need the definition cache, so I can look up type information, I think, is the main thing I need. So I can do a lower function that takes a function info and returns. Oops. How did we call it in our IR? We called it a function. Okay. So I'm gonna label those explicitly. This is an AST function info. As resolved, those can be probably imported unqualified, and that returns an IR function. And there's gonna be a lower module, which will also take the definition cache, and will take a resolved module, and will return, I suppose it only needs to return. It only needs to return a hash map from name to function. Since constants will always be inlined, the symbols that the only symbols I care about will be the function info. Oh, I guess I don't need the definition cached then. I guess a symbol cache will be all I need. Yep, okay. Okay. And this will probably need to be monadic in some way. If... it depends, actually. In theory, those operations could be total. There's no longer any risk of error. If our name checking and type checking have been correct, there is no error that needs to be reported to the user at this point, I think. The only situation I can see where we would need to report an error to the user as part of the lowering to IR is if we bundle some IR optimizations as part of the lowering, and those optimizations surface warnings or errors. Like, hey, this thing here yields a warning because we are performing these optimizations because of undefined behavior or whatever. So maybe those functions will need to be some kind of monadic to be able to report diagnostics to the user if we bundle optimizations as part of this, which we might. But that's not going to be something we do this evening, so I think for now, this is good enough. Okay. We will need a bunch of those things. Now, there is immediately something that is wrong here, which is I'm going to need to import this and this for the types of resolved module and for the symbol cache, which suggests to me that those things should absolutely be moved out of the stages things and into the representation, because the stages should just depend on the representations and not on previous stages. So I still need to do here from the AST, I will import resolved explicitly, and otherwise it will be imported qualified as AST. And the IR will be imported qualified as IR. Actually, do I do this change now? I'm tempted to do that. I'm tempted to move the things I'm going to need as part of the output of the analysis phase to a dedicated file in representations so that I don't have to include this as part of representations. So I already have a symbol, so I could put I think I'm just going to do something where I'm just going to create a representation interface. Just going to be the output of the analysis where we have built the interface of a module. And I think I'm going to rename resolved module into interface. So that means scope can stay. Scope is purely something that is internal to the analysis. But definition cache, symbol cache, function cache, all those are representations that I will need to bridge the gap between different phases. And an interface will be the result of compiling, well, analysis of a module, and will contain all of that stuff. Okay. I'm going to need a few things. I'm going to need a bunch of representations here. I'm going to put them here. Which means in lowering here, I only need representation interface. Okay. I could almost consider taking a symbol here, because some constants will become IR functions. So maybe this is actually taking a symbol. And therefore, I don't have anything of the AST directly in this file. But this returns a maybe function, because maybe some constants will not need, some symbols will not require to have an IR function associated with them, which for now is all of them, but won't be in the future. And now this takes an interface, and this returns an object, I suppose. And an object will be a hash map from name to function. And between like interface and object would be more interface file, object file, I suppose. I guess object is incorrect. The object file will be the bytecode version, not this. So I think object is incorrect. I think for the lowering into AR, I need to not use that terminology. The object file will be the bytecode version that is ready to be linked, basically. So that name object is incorrect. And maybe I just called that the IR. That is, the IR is the hash map from name to function, basically, from which is enough here to represent everything that we need and will contain everything we need to export to the LLVMAR at some later point or to do a representation of this. Okay. So I probably want to reorganize them in order in which they appear. The AR is a bunch of functions. A function is this, which contains a starter block, a bunch of other blocks which are identified by a label. Oh, I haven't defined the label actually. And a bunch of arguments and return value, which are registers. So a block is this. And then I think I'm going to put register and labels. And I think a label is just... I can probably get away with simply labeling them by number. So that means... Which means I could probably use an int map or something here rather than a hash map, a generic hash map. That means a label is probably just a wrapper around int. A register is that. A type is this. I'm thinking about like the LLVMAR will need to contain the struct definition for the struct type, but we don't need to accumulate those as part of the generation to IR because we don't need it for our purposes. And something that takes our IR and generates the LLVMAR can just like keep a cache of like we've encountered this shape of a structure. We give it a unique name based on that shape. Yeah, I think that's the easiest way to do. And I will probably need the array type or something at some point here, but we don't have that yet. I will probably also need to have a way to represent the error type, the unreachable type in this. If I look at the built-in stuff, like unit void, maybe one of those will need to have because I think unit I will not need. Those will be LED'd at this point. There will be no register of type unit, but void, that might happen. And maybe I want to keep track of this to indicate that void means something went wrong, or maybe this will be LED'd at this point as well because it's unreachable code anyway. So maybe as part of this, if anything has like a register that is type unreachable, basically. That's something I might want to think about before I start doing anything else, which is how do I handle a function call in the block that returns something which is of this type void? Because if something returns something of this type void, it means it will not resume execution, which means anything that comes after in this block is moot, is dead code. I can safely ignore it. It will never be executed. Maybe I can represent that with another terminator of another block terminator. Where are you? There you are. Here. And that block terminator will be panic here. And if I detect something that will panic, will return something that is a void, then I can just end the block in panic, and I don't need to link it to anything else. That's how it will end. Okay. Something is missing in this as well. Jump will need both jumps will need to know what arguments they're giving to. They will need to know what arguments they're giving to the block, because I'm using block arguments, not phi functions. Which means I might need something else. I might need an address. Oh, and I might need that for the types as well. Yep, function type. Oh, but if I need to have a function type, then I need to have that in the type as well. No, I think it's enough in the function type to have list of arguments, list of returns. Okay. And for the instruction, do I do that in the call, the invoke? No, that's not needed at this point. Okay. Because here, if I jump somewhere, I need to indicate what block arguments I'm giving to the target block, basically. So I will need, yeah, I think an address, a target, will be a label and a list of registers. So jump, unconditional jump is jumping to a target. Branch is branching to either target. Okay. Based on the value in a register. Okay. What am I missing? I think that's all of the types. So if we go back to our lowering, a symbol, given the symbol cache that we need for the definitions, we can maybe make a function that needs to be exported out of something. And this is not an object, this is the IR. Given some interface, we generate the IR for that module, basically. Okay. That's a lot of code for not a lot of... That's a lot of talking for a lot of progress. There's one thing I want to check. I've created this interface file. It contains my different caches and this new interface thing. I'm going to need in the analysis here to add representation interface. Actually, I'm going to need template Haskell as part of this for the lens generation, which means I no longer have it here, which is good. And that means this is maybe interface. Okay. Let's try to compile this just to make sure that all of our shenanigans with types are consistent. It is not. This is now requiring things that, yes, I have not added the new. Oh, no, it's fine. Okay, I had a moment of like, oh, we have an analysis, something in the analysis depending on another stage, but no, it's depending on something within this current stage. That's fine. Interface. No instance for show type. Deriving int. That makes no sense. Deriving show. There we go. Okay, symbol not used. That makes sense, I suppose, because I'm only using the symbol cache. And I'm only using name. Yes, okay. And symbol cache, of course, requires symbol. Okay. Oh, scope. Aha. Maybe function cache is actually. No. Ha. The notion of scope bridges. The notion of scope bridges the analysis barrier. That's kind of interesting. The interface must contain the scope of a function. And that is something that is ugly. That's because of the instantiation of generic functions. What happens when I instantiate a generic function? I redo the analysis, but this time with the complete knowledge of the types involved, which means I need to basically put myself back in the context of I am in the module in which it was defined, I have access to those things that were imported, and I redo the analysis knowing what the type arguments are. Which means I need to keep track of what the scope, the top level scope was in the context of that module to be able to redo the analysis as if I were in this and the function had been instantiated there. So scope breaks the module boundary, which is kind of weird. So scope will be something that I will have to include as part of the interface. Which is peculiar, but I suppose it makes sense. Okay. Resolve module doesn't exist. It is called interface now. And in our analysis file here, there's probably a place where I create a resolved module, which should now create something called an interface. Make lenses. Yes, that one comes from, and I can move the import. It comes from control lens. Actually, I probably still need control lens in this file because I'm doing lens manipulation, I think. So I'm just going to do this, and here I'm just going to import the only thing I need, which is the template Haskell generation of lenses. There we go. Symbol, that comes from symbol. Unimplemented actually comes from internal. Yeah, there we go. And actually, I probably don't need this qualification because the names are now unique enough. Okay, the import is redundant. That's good. symbol is redundant here because I've moved the definition of scope elsewhere, I think. Let's check that this compiles, and that should be fine now. Ah, almost. Is this in the test? No, it's not. Oh, the simplification, of course, yes. The simplification phase, which is like the trivial AST transforms. This is now interface, and that's good. It means that this no longer takes stages analysis, it takes representations interface. Again, one more, each stage does not depend on other stages, but purely on the representations that are at the boundary between them. Everything else should be the same. Except, of course, this is in the test. Okay. This is in the test. I probably need this. It depends on what is included in this file. The stages are included, yeah. It's not a very good set of things to import. I will probably want to change that at some point. But not yet, I guess. Because that's gonna be when I actually work on building the pipeline, which I don't have at the moment. So for now, this is fine. And here again, resolved module becomes interface. Okay. Ah, yes, I suppose Zeus is no longer called. I should fix that. Resmod is a terrible thing. I'll call it interface. Go. And I will have to replace resmod with interface. Okay. Compile that again. And this is still not in scope. But I have imported interface. Oh, yes, of course. I have fixed all the cases that were... Yeah, okay, that's the only one. That's fine. This is now interface definitions, because resmod no longer exists. Okay. And those don't exist because this is not importing the interface, oops, thing properly. Ah. And this one is not in scope because likewise it's missing the one import. Okay. So now this nonsense compiled. But since it's purely moving things around, I'm gonna commit it right now. So that all subsequent modifications are easier to follow. So this is a very basic introduce interface define IR. Okay. And now we can start working on the lowering functions. We might need, I mean, obviously this one will not be implemented in this module because it is too complicated on its own, and I think I'm just gonna do the same thing I've done for the analysis, create a subfolder and move code in there. However, lower module can probably be done trivially here, because that's basically a cat maybes kind of thing. Because if I look back at how an interface is defined, I will basically need to go through the symbol cache. Yeah, it is a map maybe on the hash map. That's basically what it is. So I have a symbol cache, which is the all symbols. That means I need to know. Yeah, I still need to carry around the dependencies. I cannot transform a module from its interface. Oh. Maybe I will want to change that. Maybe I will want the interface of a module to contain in its symbol cache all of the symbols it requires. Wait, the symbol cache isn't enough. The symbol cache isn't enough. That is incorrect. I need the definition cache. I need to know. Oops. Yeah, no, the reason why I need this is not because of the symbol cache. The symbol cache, I don't care. What I need to know is the type definition. I need to know about the types. And if I need to know about the types, then I need to have access to the declarations. There is something I could consider. There is something I could consider as part. A symbol is a terrible name for this. As part of the interface, I could cache the type definitions that are required. I could cache the type definitions that are required as part of this output. That will result in a lot of duplication. That means like when I cache the output of the analysis phase into an interface file, that interface file contains everything, including from its own dependencies, which means that when I load the cache, I don't have to check for the dependencies of that module which I think, yeah, is what I want. Which means I'll have to make it so that the interface contains the cached definition of its own dependencies. The question will be, can I prune them, basically? Can I keep track of the ones I have looked up so that I can prune this cache to only contain the things that I require? And should this function cache also contain... No, this function cache doesn't need... This function cache doesn't need to contain... It does. It does. If I want this interface to stand on its own as a compilation object that doesn't need its dependencies, it needs to contain the cache of functions of all of its dependencies transitively. Okay. One sec. I'll need to think about this for a second. Yeah, it will need to contain everything. It will need to contain everything it might require. However, I can probably prune them for efficiency. As in, I can keep track of all of the names I have actually ever looked up, which means, okay, this name is something I had to look up, this type is something I had to look up, which means I can only keep in my interface the names, the definitions and the functions of things that I know have been looked up. Okay, that should be fine. So I won't do that now, but let's put a note there. Especially since we're going to need that for the purpose. Well, I guess we only need that if we want to do multiple module compilation, which we can test our lowering into IR without it at the moment if we only lower one module at a time. Bundle required dependencies by one, keeping track of all looked up, of all names we have looked up. 2, doing the union with the given, with a filtered view of this function's arguments. Okay. Which means, in turn, that we can go one step further, and we don't need the symbol cache, because now our interface, I guess we still need the interface then. Our interface will contain all of the definitions that we depend on for the process of compiling this compilation unit. It will contain all of the functions we need for the instantiation of its dependencies. It will contain everything, which means at this point, the output, the interface output of something is enough on its own. Okay, so here, lowering, we take the interface and we can generate the IR, and that's it. So lowering a module given its interface, which we can name module interface, is gonna be Do I have a cat maybe on hash maps in my prelude? I don't. I thought I had. Is there one already? Hash map strict. Map maybe? Map maybe already exists. Okay. There's no map maybe M, however. So if I end up making these functions monadic, I might need to change how I do this. Okay, but map maybe already exists. So lowering a module will be a map maybe of lower function with the module interface as a first argument of the interface symbols. So for each of the symbols, we try to see if there's a IR function that we need to generate, and that gives us a hash map from name, which is a thing that uniquely identifies a symbol, to its IR version, its function definition, if any. And now, the only thing we have left to do, which is going to take us weeks, is this lower function. So I think I'm going to start writing it in this file, and I'll see how I start segmenting it and cutting it and putting in other files as I need. So this is the part where I basically have to implement this thing. And if I want to do it in one go, I have to take into account, yeah, there's a bunch of things I have to do. Okay. Well, for now, I can already start with if I look at symbol. For now, constants do not generate functions. This will not always be true. Some constants will require computations or complicated things on the stack, and therefore those will be implemented as a actually this is maybe not true. Maybe I will want for like I was gonna say like for strings or anything like arrays, things that do complicated things on the stack. I don't want to like inline that code all the time. Maybe for now I'm just gonna leave it like this, but maybe even for ints, since Piètre is very limited in how some functions are some constants. Actually, maybe I don't want to encode the fact that like constants depend on their type at this level, maybe not at the level of the IR. Maybe I will want to make all constants like this and do the constant inlining at a later phase. That being said, I'm already doing constant inlining for int values as part of the analysis. I'm already doing the unfolding there. Maybe that means I shouldn't be doing the unfolding at that point. Maybe I shouldn't be doing the unfolding in functions as part of the analysis, so that when I arrive here, constants in functions are still values I am pointing to, and I can choose when doing code generation. But I guess it doesn't make sense to do the code unfolding as part of the code generation. It makes more sense to do it on the IR, which means which means that actually the fact that some constants will be implemented as functions might end up being an implementation detail of the code generation phase, where like, oh, I have this constant, but I actually want to move it to a dedicated symbol so that I don't have to inline something that for this specific backend requires a lot of operations. Maybe that's the trick. So that means it's still fine to do constant unfolding as part of the analysis. The AST contains just constant, the AR contains just constant, and the code generation might generate more. But if the code generation ends up generating new symbols, that's going to be tricky. But that's not the end of the world. So I think that's the right approach. Which means constants do not generate an IR function. That is purely a implementation detail of the code generation for a given backend. Therefore, we can go one step further. We are not even taking a symbol. This takes a function info resolved. Which means we are back to needing the AST in scope here. This just takes a function info. Okay. Which means here I can rewrite this as a flip map may be. Here's the map on which I'm doing the map may be, and the function I am using is this case, where if the symbol I have is a... Or maybe does that mean I just don't need to keep constants as part of the symbols? I think that might be it. I think this might be it. I don't need to keep the constant as part of the symbol. I can remove symbol altogether. Goodbye. As part of the interface, the symbol cache is just a hash map of name to function info resolved, stripped of location information. Okay. So no need to do a case here. So this is back to being a map maybe, and this is back to being lower function of the module interface. No need for a case. There are only functions at this point, and that is indeed. And maybe no, I think I want to expose lower function as a top level thing, just for the sake of tests, I think. Okay. Next. What is a function info? It's this thing. It has a name that I don't care about for the purpose of this. It has a type, and it has a body. The type is the return value. Wait. Oh, no. Type is this thing that contains the parameters, the arguments. Okay. So the parameters I can safely ignore. I could add a check for a sanity check that we never end up with a function that has... I can do that actually. Reduce this a tiny bit. So here I have a function info, and I'm just gonna expand. And when not null the fun params of the fun type, report ice. Because that means we somehow ended up with a generic function within. We somehow ended up with a generic function in the symbols of a module, which makes no sense. We cannot instantiate generic, like we can only have instantiated functions, which means they no longer have type parameters. So we can do that. What's the things again? Okay, I think that's fine. So what are we going to need to do? We are going to need to create from this function type. We are going to need. Where are you again? You are in IR. We are going to need to create an equivalent function thing. The first start will be the first block, which we can start going through. And I guess the things we need is the arguments, the registers. But I think then from the very beginning, I'm going to need to keep track of the states of my different registers. So I am going to need to immediately start doing some kind of state monad to keep track of this. Except actually the return thing is not going to be the registers, I think. Yeah, the return thing is not going to be registers, it's going to be type, I guess. Do I need that information as part of this? Do I need that return type information as part of this? I probably don't. Since all type information will be gathered from looking up the function info in the first place. So maybe I don't care about that. I guess I only care insofar as I want to be able to generate the LLVM IR from this IR representation. And that's not something I really care about at the moment. This is something I'm willing to modify the IR at a later point to make that generation possible. So maybe for now, we don't need that. Okay. Okay. Then here goes do the thing. I guess I can use unimplemented as a placeholder. Okay. So I suppose now I'm going to introduce lowering as a module, and I probably want to have a monad thing in it. That will contain Are interpreters state machines? Some of them might be, I suppose. I suppose so, yes. In the sense that like most of them keep a state, and you can represent most of them as state machines. That doesn't mean they're not necessarily implemented as such, but yes, you can see an interpreter as a graph from different states, with each instruction being a transition from a previous state to a next state, which I guess is a state machine, yeah? So from an implementation perspective, not necessarily. From a theoretical perspective, I don't see why you could not conceive of an interpreter as a state machine, yeah. Okay. So what will we need to keep track of? What will we need to keep track of? Look at how we defined our analysis monad. Copy, no, all of this is way too complicated to what we need. But I guess it's going to be along those lines. Yeah, I'll just copy that and get started with that. So our lowering monad. I don't think we need an RWS. We don't need to write anything. We don't need to write diagnostics as part of this phase, at least for now. We don't need an ABT. This is a total operation. There's no risk of it failing if we have done a proper job of analysis. If it fails, it's an internal compiler error. It's not a user error. So we don't need that much stuff, I suppose. I guess we will need to have. I guess we'll need to have a reader T of the interface, because we're going to need to check a bunch of things in it anyway to do lookups and stuff. And we probably want to do that on top of a state monad that will contain something. Now, of course, from an optimization perspective, I could want to use the st monad underneath rather than using the state monad, or just IO and references, but I think for now, I would rather keep it pure and just use a state monad. So the interface is enough. I don't need anything else. Although I will need, actually, I will need one more thing, which I am going to put in the interface. I think the interface would need to have the module name, actually. Which means in the analysis top level function, when we create the interface, I will need to add interface name. That's going to be the module name. That should be in scope. Yep, perfect. That way it is accessible as part of this. And here it is. Okay. Now, what state do we need to keep track of? We will be doing blocks one by one. For each block, do we use a different state for each block? No, the state will be shared across the different blocks of the function, because I need to know where registers come from. So that means I will need to I will need to keep track of how I've named the registers. For instance, oh, here I'm using variable x. Variable x in this IR will be known as register whatever. So it's going to be a hash map from role to a register. I need to keep track of the number of labels I have accounted. I suppose next label is enough. As in, whenever I need to create a label, what will be its index? Which is just gonna be a label, I suppose, or it's gonna be an int. But I will do the same thing I did that for the other one. I will hide that lens. I will not export it as part of the module. And I will need to do the same thing in the next register, which is also just going to be an int. And I will need to keep track of from which blocks do we arrive at a given block. So if I am on a given block of instructions, what parent blocks do I have? Which ones end up in a jump that might end up where I currently am? Which one ends up on the go to, or which one ends up on, like, for instance, at the end of a while loop, we could be coming from the condition block because the condition was false. We could be coming from the inner block of the loop because a break could bring us here. Like there are blocks that will have more than one parent, which is where the phi functions / block arguments will be required. And I think I don't need to keep track of the outgoing edges. Those will be recorded in each block as the terminator instruction. I only need for this, for the lookups, to know what the parent is. And there might be cycles, so I will need to be careful with that. So, I don't like this L state prefix. I'm just gonna say ls for brevity. And the parents will be a hash map from... Oh, does that mean that every block needs to have... Yeah, every block needs to have a label, which means the starting block will need to have a label as well. Which means I might need to keep track of the current label as well. Or no, I might not need to. I will probably have one function for the current label rather than putting it in the state. No, I will need to have... Yeah, okay. So the parents will be, for a given label, which uniquely identifies a block, a list of parents of labels. Some of them will have 0 parents, like the starting block. And some will have... Most will only have 1, I guess. Is that true? Yeah, I guess it's going to be 0, 1, or 2 parents every time. Okay. And I probably therefore need the current label, which is going to be a label. None of that is required, and it all goes away. Context isn't required, it goes away. Lowering state is the only lens I need to generate. And I am going to need to have in scope the IR. That might be about it. No, I'll need the interface as well. Okay. And I will probably want to not export everything. I think I will want the lowering monad to be opaque so that the implementation details are hidden within this module. I will probably need a run lowering function that I haven't implemented yet, but I will need. I will probably need. I might not even need to export the lowering state as long as I have the lenses exported, actually. Because creating the initial state will probably be done within this module and doesn't need to be exported. And yeah, I think all of the internal logic will be done within this module. So I think I'm not even gonna export the lowering state at all. Okay. Which means I only need to export the generated lenses. And that's not all of them. The next ones will not be exported. Or current might be enough. I'm almost tempted to not even make the current. No, I will need to have access to it. Okay, that's fine. Okay, so what am I missing here? I am missing make label, make register, and a run lowering. So what do we need to run a lowering? We're going to require the interface. Oh, I need to fix something in the IR as well. Because now a function doesn't have a starting block, it has a starting label. And then all the labels are in the hash map from label to block rather than having the block here. Okay. So now to run a lowering operation, we need the interface. And that's basically it. We don't need anything else. So then we get some lowering M operation, which returns some kind of A value, and we return that A. And run lowering of an action is that action, and we run reader T with the interface, and we flip exec state T or eval state T. I think exec. I never remember which is which. Nope. eval state with the initial state. And what is going to be the initial state? It is a lowering state used within our state monad. And it is an empty map of registers. And I can probably just use MMT to avoid more imports. The next label is gonna be the value 1. The next register is gonna be the value 0. And the map of parents is going to be an MMT as well. Oh, or since I keep track of the current... Since I keep track of the current label, do I need to start Yeah, I think I need to start instead. I will need with a map that states that the start of the lowering, the first label, the first block, doesn't have parents, and that will be the current. So the start label, and the value will be an empty list, and the current will be the start label. Start label is a label 0. Okay. Okay. To think for a second. Yeah, I think this is fine. I'm trying to think about how do I, like, is this problem with the current label going to be a problem? I don't think it is. I think it's fine. If it is, I'll change it, but I think it's fine. Now, the only thing I need as a result is make label, make register, which are going to be the only way that the rest of the code can interface with that thing. And make label is simply going to be... Will this be a problem? It should be fine. I hope I don't need monad fix for this. It's gonna be given a set of parents, give me a new label. Yeah, no, that's gonna be a problem. It's fine, I know how to fix it. And that is gonna be within a monad, which happens to be... Yeah, I don't need to do that. I can keep it specialized. So what do we do with this? I get the current value for the next label. So that use ls next label. That gives me the value. I modify it plus equal 1, so that the next label is increased by 1, and I return pure of this label of the index. And before that, ls parents is modified by doing an insert of that for that label. Its parents are the parents that were given as an argument. And then I return the label. Okay. Okay, so that all of this index tracking is kept as an implementation detail of this module and is not part of the like the rest of the code doesn't have to care, doesn't even have access to the internal index, and as far as it knows, labels are purely an opaque thing. Okay. And I will need a somewhat similar thing for a register. A register is an index and a type. I will need a type to create an opaque register. Give me a register of that type. And this is going to be very similar. The index will be next register. The next register is going to be incremented by 1. Here, I don't have to do any bookkeeping of a hash map or something like... Oh, actually, that's not true. Do I need to know how it's... Nah, it's probably going to be done by the caller. As the caller gives me, like, ask... Like, I need a new name for a register, give that to me. And then the caller will be able to say, okay, actually the name, the role for that register is this. Yeah, because I will need to do the lookups. I will need to have access to that. Yeah. Or maybe I keep this as an implementation detail of the monad, which might be... No, I think I want to keep the register lookups and everything as part of the lowering, not as an implementation detail of this. So no, I'm not going to do the insertion there, which means, yeah, that is it's going to be purely pure register index type. Okay. And I will need a few things. Actually, it's a typo, yes. I don't need the deriving. This will have the monad fix instance I require for generation of circular labels. Because here, I need to know the name of the labels of a parent to be able to generate a parent. So for cycles in the graph, I will have issues, but that's fine because I can use monad fix to recover laziness in my monadic context because I don't actually evaluate the labels to be able to actually work. The only thing is, if I'm using a static state monad, I might not be able to do that. I might have to make one of those things lazy. Actually, let's try that immediately. Let's try that immediately when this compiles. Yeah, simple symbol no longer exists. Oh, that means there's a few places where, oh, this is equal, not this. Also, I suppose in the analysis symbols here, module symbols. Okay, so in the monad, the other monad, the symbol cache here for in symbols, I should probably. I don't do anything here. Okay, so it's gonna be probably in the analysis thing here. Oh no, I probably do it as part of the core. Let's see. This would probably be in the top level analyze declaration function, analyze definition, sorry, where at the end, yes, here I insert thing in the symbols, but this symbol is not required because I do not. So this becomes just a const def, like it becomes the same thing as the others, which is nice. I'm going to vertically align because at a better resolution, it's more readable. And here, symbol function no longer exists. This is purely the resolved info. Okay. And that means I can remove this. Okay. That's because I did not enable template Haskell as part of this module, and I will need to import control.lens, and I will need data hash map strict qualified as M. Role comes from representation and name. Oh, those require the use of the lenses, which have not been declared at that point, so here they go. No instance for hashable label, that's a good point. That's trivially fixable, however. In label, where are you? I will just need hashable here, which is trivial. And of course, EQ is required. That makes sense. I assume this is registers per rule, yeah. Okay. This binding for index shadows, I'm just gonna hide index because that's a good variable name, it's descriptive, so I'm just gonna do that. Symbols no longer exist. Symbols no longer exist. Oh. Define but not used. That's a good problem to have. Yes, since it's not used, I get a warning. That's fine. I will do that for the moment. Now, what I want to try is something like this. I want to check what state needs to be lazy for this to work. I want test to be a function that gives me a list of label, and test will be obtained by doing a run lowering undefined as my actually it's an error. Hello. A strict interface, because at the moment I don't do any lookup in the interface, so I think it's fine to leave it unevaluated. And what I want to do is this. I want to test creating a cyclic graph using monadfix, which means doing the following. A is make label where the parent is C. B is make label where the parent is A, and C is make label where the parent is B. And as you can see, I'm using C here before it appears here, which is fine as long as this can be evaluated without, creating infinite recursion by the power of monadfix. And here, let's say that I return A, B, and C. Now, I suspect that this is not going to work because I suspect that since the state is strict, I'm going to run into issues. So I think to fix this, I might need to change something about the lowering state. Let's try this in GHCI. Is that the stack GHCI? It was. Okay. Let's finish this until it compiles. There's an error somewhere. Intent to use recursive do. Is it not enabled? Oh, interesting. No, I want the documentation. I can't type. It's too late to type properly. Okay, I am looking for recursive do. Is that... Yes, that's the one I need indeed. That introduces the mdo keyword. It's not enabled by default. That's probably not a bad idea. Recursive do. Define but not use test. That's good. It means it compiled otherwise. I'm going to export it here for the moment. Okay, that compiles. Stack GHCI, let's go. It recompiles everything because the options are different. That's going to take a while. We're starting to have a non-insignificant number of modules in this. Okay. So, if I call test, yep, it is there. And this... Oh, no, it works without the lazy state. That's fine, then. So this worked perfectly fine. This worked perfectly fine, where I did A is make label, B is make label, C is make label by referencing other labels. And it worked just fine. However, yeah, I think I'm gonna here instead return a hash map from label to label so I can see the parents. And which will be, instead of doing this, this will be a use ls parents. Let's see if this poses any problem. Nope, it still works. Labels 0 has, because yes, by default there's always a label 0, it's fine. Label 1, which is a, has parent label 3, label 2 has parent label 1, label 3 has parent label 2. That works just fine. And I can even make them their own parents if I want. And I can even make all 3 the parents of each. Label 1, which is A, has parents label 1, 2, 3. Label 2, which is B, has parents label 1, 2, 3. That works. Okay, perfect. That means I don't need to make anything lazy. This works as is. That's great. Thanks, monad fix. Thanks, recursive do. I don't need to do that here, though, but I will need to do that as part of the lowering. Tests can go away, and I think we have all we need for now. Okay. How do we do this? I suppose we're gonna need a lower block function, which is gonna be operating within our lowering monad. And it's gonna return a block, I suppose. And what does it need as argument? It doesn't need the interface, which will be part of the lowering monad thing. It's actually called lowering M. I will need to know the name of the label. Like, here's the label I need to... Here's the label I need. Oh, come to think of it, I will probably need to... I said earlier, this part of the code cannot error because we are past name checking, type checking, all of those things. There is no more errors that can happen coming from the user. Any error we face would be errors coming from our code. So there's no need to have a proper error reporting mechanism. At this point, if something goes wrong, it means there is a big bad bug in the code and we can just panic. There's no error coming from the user input, which is important. However, that doesn't mean that we won't have diagnostics. We could still have warnings. For instance, unreachable code might be a warning we want to emit. Like, hey, this line there, no, nothing will ever reach it, which might be something we want to be able to report. So maybe it means I go back to my previous thing. Okay, so I'm going to comment this out for now. Which means diagnostics is going to be something that needs to come out of the analysis to be something that's common to different parts of the compiler. I don't want to do that now. I'll do that later. For now, no diagnosis, no warnings, no nothing. I will do that at a later point. Okay. So. This will need to take the label of the block that we are currently going to create. It's going to need to take... It's going to need to take... the list of instruction. It's going to... Yeah, it's going to need to take the AST block, I suppose. Although it might need to take a partial one because a AST block will be decomposed into multiple blocks. So I suppose block, do I have? Yeah, it's just a list of statements. So I guess an AST block is that. It is a... I don't have actually a type for this. Should I have one, actually? I'm tempted to introduce one, actually, yeah. A block is a list of annotated statements. And now, annotated statement. Actually, let's do this as annotated statement followed by some non-space is gonna be replaced by block of this. Not here. Not here. Not here, I think. However, that was wrong. Okay, so let's do it again. Okay, so this is gonna be become a... I'm wrong. I should probably not do it with regexes just because this is getting too complicated. Okay, so what I want to do is this. A list of annotated statements become a block. There we go. Not here, but here, and here, and here, and here, and here. Okay. Okay, that should be fine. Is there any other place in the code where we have... Nope. Okay, perfect. So I just see if that compiles. In the meantime, I go back to here. Oh, hello. How are you? So here, lower block will take an actual block resolved, which I think I can import. So this is going to be qualified as AST. This is going to be resolved, which is the list of instructions. Where does this block of things that we lower into the AR start? What label is it? Which we'll have created ahead of time. Yeah, sorry, if you arrive in the middle, this is going to be nigh incomprehensible, I'm afraid. But welcome nonetheless. I am doing the part of, we've already, as part of the compiler, done the lexing phase, as in given some source code, what are the key components? This is an identifier, this is a number, this is a symbol, this is an open parenthesis, that kind of stuff. From which of them the parsing, as in, this sequence of symbols is the definition of a constant or the definition of a function or a statement or something like this. After this, we've done the analysis. Do the names check? Do the types check? And now we're doing the lowering to IR, as in, okay, I have this abstract syntax tree that represents the source code we've parsed and checked. Now we need to generate a lower representation that can be in turn analyzed for optimizations and then generated into code. So we're doing this lowering to IR phase at the moment. So here, this function will take the label, which is going to be the go-to label in the, if we generate some LLVMIR, where we would be, or in the assembly, if we would be generating assembly, which we won't, but in principle. The list of instructions that we're trying to translate, at least where we are, and we'll return the generated IR block. Did this compile in meantime? Nope, it didn't. Yes, of course it didn't. Let me just do unimplemented here and go to the first error. So this should be a block here. Okay, is that the only error? Should be fine then. Oh yes, of course. This is not something I can import directly. I need to import AST phase. Not like this. Like this, I believe. Okay, so now I should be back where it... Not yet. What's missing? Oh, yes, of course. This is an AST function info. I have imported things qualified. And this is an IR function. I will probably want to be very clear about which, since I'm going to have names that are very similar, function info from the previous phase, function as the result of this one, I will probably want to be very clear about using a qualified name to make sure that the code, that we know what I'm talking about. This is the thing coming from the AST. This is the IR. Here, likewise, it needs to be decomposed like this. Okay. The constraint foldable. Interesting. Fun params is... Oh, I probably don't have... Yeah, of course. I'm going to just do that. Which means I don't need to use AST for the things that I don't need to, and those things will now be in scope. And this should now compile. There we go. Now we're compiling the tests. That's good. Okay. So what do we do when we try to analyze a block? We need to have the label as argument. So the first thing we're going to do is set the current block, which I think is how I've named... No, just current. So okay, what we are currently doing in case, and that's only in case we end up needing it for more than one function, the current happens to be this one. There we go. No. It is this operator. There we go. And I will need the instructions. Now, can I do this with some kind of fold? I don't think so. The problem is that at any point, I can encounter a branching instruction. I can encounter an instruction that signals the end of the current block and the opening of a new one, which means at any point I might encounter something that stops the block where it is, which means I will need to do the recursion over the list of instructions manually. So go instructions. If we end up on an empty list of instructions, what does that mean? That means that we did not encounter any kind of terminating expressions. We did not encounter an if, we didn't encounter a while, we didn't encounter a for loop, we did not encounter a return, a break, a continue, anything that makes us like either go to another block or leave the function altogether. That means we have reached the end of the current block. That means we have reached the end of the current block, but that's not necessarily a problem. Not all blocks need to finish with something. Do we need to check the validity at this point? And I think the answer is no. Is Haskell easier to write a compiler in? I would argue yes, but that's because I'm already familiar with Haskell. Haskell is fantastic for that kind of work, but it doesn't mean it's necessarily the best. The best language for a given task is not just a property of the language, it is also a property of the team that's using it. So the best language for you to write a compiler could be the language you're the most familiar with. But if we don't take into account knowledge of the programmer, yeah, Haskell is very suited for that kind of work. The only issue I would highlight is some of the literature around algorithms for stuff like register allocation or IR lowering and like conversion into a single static single assignment form. Some of those algorithms are described in the literature in a stateful form, which Haskell is less suited for. But otherwise, no, Haskell is definitely like AST manipulation is what a language like Haskell is made for, basically. And yeah, writing in C, well, you have the upside of everything is going to be very fast if it works. But yes, you are going to be lacking some of the convenience of Haskell for sure. But yeah, I'm thinking here in the case where we run out of instructions, I think it's fine because again, at the end of the block of loop, we already know where we're gonna go, and that is a property of the block that I will know from the color of this. This will not be a property of. Wait, there's an issue. Sorry, I'll answer you in a second. I'm just thinking out loud. When this function aims at creating a block, which is this list of instructions and a terminator at the end. And the terminator is either jump to a target, unconditional jump, branch, return, or panic. However, if the list of instruction ends without encountering an explicit terminator, I didn't encounter a return statement, a branch statement, a break, a go to, like anything like this that would allow me to say like, oh, we're going there next. That means that where we're going next depends on the caller. But this function must return, not this one, this one must return a block. So it must decide what the terminator is in the case where we don't have something. I guess I can just say panic by default if we did not encounter an explicit termination and let the parent that knows the context, this is the overall function, therefore, if we arrive at the end, this must be a return of a unit type, or this is a while loop. The default thing is a continue, it is a jump to that particular label. I can let the parent override the result of this block. Okay, so the thing is, like, you're caring about performance is like really a C concern. Here in Haskell, at the moment, I absolutely don't care about performance. I'm using linked lists for a bunch of things. I will care about performance later. For now, making it work is the first step. Making it performant will be a second step. But yes, I would really recommend getting like your API for your different stages as clean as possible so that then you can change the internal representation to whatever you want without changing the shape of the API, which means you are able to choose whichever representation works best for your performance concerns or representation concerns without it impacting too much the rest of the code, which is what I'm going to try to do here as well. So here, actually, do I need to keep track of the current mess that is the block? because the block is again all of this nonsense. Ah, yeah, yeah. If you're embedding in the web server, yeah, you absolutely care about performance for sure. Haskell can be performant, but it's like it is a compiled language that can be fairly performant. It's just that if you write things in a naive way, they will not be that performant. Performance is something you need to put some effort in. Thankfully, it's not that complicated to make things performant after the fact. It's mostly changing the type representation and tweaking a few compiler options, which is why for now I'm not caring that much. It's because the high level structure of my code will not change when it's time to like optimize for performance. Yep, that is a sum type. It's not the best, but it is going to do the job for this particular thing. So a value of type will be one of Haskell is extremely clean. Like a tree type, like this is a tree type where a value of this is either one of those leaves or one of those values that contains types recursively, and that's how a tree of things is represented. Haskell is extremely clean, and the thing I personally love a lot about it is, yeah, sure, if you want. A thing I absolutely love about it as well is that the core language, without all the extensions, the core language is extremely simple. There are very few things that are not defined, that are like part of the language that are not defined in terms of the language. You have like data type definition, function definition, and most things, and type classes, and most things you will ever encounter are defined in terms of the language, not defined in terms of like built-in things that the compiler has access to. And that means that a lot of the basic stuff is extremely simple. Let me have a look. Good old C enums. I'm gonna be honest, I don't miss C. C is it's fun, it's good to know. I don't miss it. Okay, so I will want this function to create a block. Creating the terminator element can be done at the very end when I encounter either the end of the instructions or an explicit branching instruction. The arguments can be determined ahead of time, I suppose. No, actually, they cannot. I will need to keep track of the current arguments. Okay, so that's when I go in the statement as well. Because the block arguments are gonna be determined by, okay, I encounter a reference to a register that is not defined within the current block, meaning I have to go look for it in the parent blocks. And if there is more than one parent that returns a match, that means that I need to introduce a block argument and I need to go modify the parents as well. But I only need to modify the terminator in the parents. Okay. Okay. That's based, your comment about using a VH for my side is based on my accent, I suppose. Because, yeah, my accent is a dead giveaway. Yeah, I've been surprised to see that their offers are like the pricing and the quality of the offer depends a lot on the country. Like their French offers that I'm still on despite no longer living in France are cheaper and better than the Irish offers. So, yeah, I'm still using it. It's convenient. Okay, I'm just trying to think out loud. I will need to keep track of the current state of the block, which means keeping track of the current registers in the block so I can do a lookup there. Ah, nice. Actually, do I need do I need to capture the registers as part of the block, or which registers are defined where is purely an implementation detail of the lowering and doesn't need to be captured there, but needs to be captured in the state? I think it's the latter. I think when the IR is generated, I don't care about the registers that are defined in the block. They will be the instructions basically. Each instruction will be something that creates that fills a register basically. Almost all of them. That means that's an implementation detail of the lowering algorithm, which means it needs to be tracked. It needs to be tracked in the state. Okay. Okay. So here, the state I'm carrying around when doing the analysis, I will need... Oh, but this hashmap rule register, that is incorrect, I think. Or is it? Variable x in this context, I'm looking at an assign y is x plus 3. I need to know where that x comes from. And that x will have been given a register name as part of the process. This is what this hash map captures. However, that capture of this is where this value comes from needs to be in a block. I need to So there, this paper that I'm using as a reference is using a double like key for the map, which is, okay, this variable I'm trying to read for the current block contains this value, which is just going to be for me, what register do I have associated with it? So yes, I think this association needs to be per block. So it means I think this needs to be something that knows, okay, what is the current block? Is there a value for this in the current block? That is how I will be able to differentiate and between something that comes from a parent block, which requires a block argument, versus something that was defined as part of the current block. Okay. Now, do I need to keep track of anything else? I will need to keep track of the accumulated arguments, I think. As in, oh, this thing, this role variable thing I'm looking up comes from more than one parent. Therefore, it requires a block argument. Therefore, the current block I'm building will require having that as an argument. Therefore, I must go modify the parents to change their terminator. And this is where we have the problem of the cyclic graph, which is that I cannot change parents that have not been processed yet. This is what the paper here describes as handling incomplete control flow graphs. But they use that with phi variables, which I'm not using because I'm using block arguments. That means I might need okay, yes. So I know what argument the parent will need to call me with. Oh, but I don't know yet. Okay, that's why they have a simplification phase. If my parent is incomplete, I cannot know yet if I require an argument. And by default, the answer will be yes, because any variable could be coming from it, which means I will be creating a bunch of arguments. And then, when I do the processing, I might realize, actually, no, I don't. So I will have to have a simplification phase on the block arguments. I might want to see if there is a revision of this paper that takes into account block arguments. That, or I do the transformation into block arguments at the end. When I seal a block, I transform its phi variables into block arguments. Maybe that's the trick. Maybe I keep track of the phi variables the same way they do. The only tricky thing means the sealing thing needs to transform the phi variables into block arguments and go modify the parent terminator. But this is fine because if I seal a block, then all of its parents are sealed. Okay, that's the way to go. That means that I am gonna keep something else here than just the current label. I'm gonna keep track. No, I'm gonna need to keep track of all of the open blocks, and the open blocks, the blocks that I have not processed yet. This is gonna be, how does the paper call them? It calls them incomplete. So I'm gonna call it incomplete args for now, which is gonna be for a given block, so as a label, as a key. What will the value be? It will be the list. It will be for each register it will be the same thing as this. It will be the same thing as this. It will be for a given role in a given label, a list of parent registers, of value registers. It will be actually a hash map of parent label to register. So this is the representation of the phi values of this paper, which is in static single assignment IR literature, a thing that says, okay, if we're coming from this part of the control graph, then this register contains the value v1. If we're coming from this part of the control flow graph, it contains v2. Basically, what it is initialized as depends on where we're coming from. This is what a phi variable is. If I look at the example in the graph here, they have like an x initialized to something. Let me zoom this so it's readable on stream. And a while block that contains an if that might modify the x. This results in this control flow graph where v2, which represents one particular view of this x thing, is either v0 if we come from before the while, or v3, which is the possible thing of the if there, if we're coming from the while loop, basically. That's what a phi variable is. And I don't want to use phi variables in my IR. I want to use an argument. So basically this block here, which would be the start of the loop, would have an argument which says what is v2 initialized as, basically, which is a transformation from phi variables to like another representation. However, I am going to keep track of them as if they were phi variables, as in from which parent is which value, basically. From which parent is which value, and oh, there's one thing I have to. Do I need? Sorry, I'm stacking a bunch of thoughts at the same time. I am also maintaining here a list of parents, as in, given a graph like this, a control flow graph, this block, which parents does it have? Well, this block can be reached from this one and this one. However, if I have a loop that contains a return statement, or for instance, a loop that contains a return that's not in an if, so the loop will only execute once and return immediately, basically. We are never gonna go back here. This arrow will never exist. However, should I remove it from my graph, or can I keep it? In theory, I think I should remove it, because if there is an unconditional jump there, like a return, then I can get rid of that arrow, and that means that I know for a fact that everything comes directly from this, and therefore there's no need to do phi variables and analysis like this. It's going to be a lot easier. However, I could also decide that I don't remove the arrow, because the only thing I will need to check the parent for will be... Yes, I suppose it's fine. Even if like this while loop contains override the variable and then return, which means the overridden variable will never be read, I will therefore need to do the whole phi variable into block argument kind of thing. However, I can then do a phi variable simplification phase, block argument simplification phase. If all of those are initialized with the same register, then I don't need to use that as a block argument, and I can always directly use the register, and I will be able to realize from this block, oh, this block call does not call this label, does not jump there, it jumps elsewhere, therefore it's not a parent, therefore it can be removed, therefore I can do the analysis of the phi variables block arguments without having to take it into account, therefore I can do the simplification. Okay. Okay. I still need to keep track of the incomplete args, basically. And I might need to keep track of which blocks are finished. the sealed blocks will be all the blocks that I have, all blocks that I have already finished analyzing, and their parents are also sealed, so there's no risk of any further modification, which means I can already at that point have done the simplification of the block arguments, which means it will be a hash map from label to block. Okay. Okay, there's a few things I need to change. I've said a bunch of things I need to actually make it work. As incomplete will be initialized as an empty hash map. There's no need there. Current will still be the start label. That's fine. And sealed will start as an empty hash map, because at first there will not be any sealed block. This changes a few things already, because lowering a function becomes that becomes there's no longer a need for a a maybe there, because all functions will result into a function info, so there's no need for a maybe. So this is no longer a map maybe, this is purely an f map. Or traversed at some point when this is monadic, but it's not. This check, yes, I guess I could make it as a guard on the function. And technically, I don't really need to do that. That's, yeah, I don't need to do that. So lowering a function means lowering the start block, and since every time I finish to process a block, I will try to seal it, which what about cycles? Can I seal a block? Because since I have cycles in my graph, what does the paper say? Ah, maybe I'm reading this definition incorrectly. Sealed is not exactly the thing I want. I will always know all of my predecessors because I always know I can always create them ahead of time, create the label for them, which means it's. They differentiate between sealing and filling. So we feel this, but we don't seal it. We seal this because we know it's coming from there, but we feel it. Okay, I see. I see. Ah, I see. That, I suppose, answered my question about what do I do if I realize a parent is not actually a parent. In this logic, the parent is added after the fact, like I start with the while header that I know will have maybe a second parent added at a later stage. Oh, I need to rethink a few things. Okay. So I process a block, and either I know that more parents can be added later, as is the case with the header of a loop, or I know that I have all of the parents. If I know that I have all of the parents, the block is considered sealed as per the terminology of this article. And that means I can know for sure where the variables that I have to look up come from. They come from one of the known parents. No known parent will be added later. Okay. And what does filling a block means in this context? Is it just to label to keep track of all of the registers and do this register mapping kind of thing? I think it is. Yes, that's what it is. Okay. So I guess sealing will be the operation by which I transform my phi arguments into my phi functions into block arguments, because I can just go recursively to the parents and modify the terminator thing. And given that the value will be known by then, yeah, that's fine. Okay. So what does that mean? It means I need to keep track of whether and I think that is the thing that is in here. Am I in a sealed block? And that's okay. That's what it is. So if I am processing a block that I know is not sealed, I don't have the list of parents yet, then all variables are phi variables. And then it means I have otherwise I can immediately go read the variable. Okay. Otherwise, I need, and when I seal the thing, okay, let me think for a second. How do I model this? Now I got it. Now I understand how the algorithm works. How do I model this? That basically means this lower block thing will need to know, am I processing a block that is sealed or am I not? And I suspect what that means is when I encounter something that needs to be a register, I do a lookup of it. If I am not in a sealed block, if I can determine this, then every single thing, maybe not the local ones, I guess. yes, the local ones are fine. I can immediately know, like if I do let x equal 3 and then let y equal x plus 3, I know that the x I'm referencing is the one declared on the line above. I can do this already. However, for every single register that could be a phi variable, I don't do recursive lookups because I cannot. Because I cannot. And I wait and I register them as block argument candidates. Basically, this variable will be coming from the value from the as an argument from the thing. And then when I've processed all of the parents and I know it for sure, I can go seal the block, which is to look at all the arguments, look at all the parents, and transform that list of arguments as into a list of block of yeah, okay. I think I got it. The big thing will be I will need a simplification phase because this is going to introduce a bunch of unrequired registers. Although I suppose the register allocation would already take care of that, but it might as well do a simplification phase. Okay, so there's a few things I can already do. I can already write the lower function interface. Because what it do is run a lowering thing, because all the context is local to that with the interface as an argument. And what do we do in the context of this monad? We purely lower a block. I guess lower block doesn't exist anymore. Do I fill block seal block? I suppose I do. So I get the current label, which is a start label. I fill block with the start label and the set of instructions coming from the function info, which in the AST is function info. The body. And then I seal the block. Actually, no, I'm going to do a lower block function. Because I will probably want to some blocks will already be sealed by the time I start processing them. How do I register this? Do I keep a hash set? How does the paper do it? Yeah, they just keep a hash set of sealed blocks. Yeah, I suppose that's the way to do it. Okay. So going back to this place here. Oh, I guess sealed. That's a thing. It can't be a hash map from label to block. That doesn't make sense. Because I can seal blocks that I haven't filled yet. So sealed will be a hash set of label. I will keep track of the blocks that I have finished, which is a hash map of label to block, but that is not the same thing as this. I can have a block that's sealed but not finished yet. Okay. I guess I know that the very first label, it's probably, I'm not going to put it immediately. I want to leave it empty for now. Sorry, this stream is dense. We're doing a lot of things. And I'm also thinking out loud reading a paper that most of you haven't read. Sorry, so this might be the link for the paper in question is in the description, in the documentation of the project. Please do read it if you're interested. So I am gonna write at some point a seal block function that, given some label, will perform something in that monad and probably return nothing, because sealing a block means purely adding it to the list. So ls sealed is modified by doing an insert of the label and doing a bunch of stuff that we're not going to do yet, which is the validation of the phi variables and all of that stuff. Transform incomplete phi variables into block arguments, if any. Because I might not have any block yet, because I might seal a block that is not filled yet, which means I don't have a definition for it. Okay. So I get the start label. I seal the block immediately because I know all of its parents, and the answer is it has none. And then I start lowering the block, or I guess to use the terminology of the paper, this is going to be the filling function. At the end of which I will have created a block that will contain a list of arguments. Wait. This is the issue with my representation, I think. Can I create a block that is not sealed? Can I create this block value if the thing is not sealed? I think the answer is yes. And it's just that if I seal it afterwards, I need to rewrite this block definition. Or not rewrite, but deduplicate, simplify. Yeah, I suppose it's that. Basically, it is modifying the block to put the arguments there. And for each, and that's the thing, I don't put the arguments ahead of time. I leave them unset if the thing is not sealed. And when I seal them is where I add the arguments by doing the recursive lookup, which is this. For each parent, look at the operand and then try remove trivial phi. Okay, that's how we do this. Okay. So this will be, was the block already filled? Do I have block information for this? This will be a uses of the ls blocks. And what I'm going to do on this thing of the state will be a lookup of the label. When this gives me a just value, so I have found a block, then I need to do the operation of transforming the things I have labeled as probably block arguments into real arguments or not. However, that means I'm also going to need to transform the instructions. Because if for a variable I realize, okay, this thing I'm calling v4, it is something that is coming from either of those two things. It is a block argument slash phi variable. If I realize it's not needed, then I need to go replace all mentions of that register by the actual value for simplification. Yeah, that's fine. Yeah. That means iterating over the lists. There's going to be a lot of things to do here, basically. Okay, it's fine. I'm going to do all of it this evening. I am looking for when just m. It exists. Perfect. So when just m of this thing here, so when doing this monadic operation that performs a lookup in the current state of my monad gives me a block, so it was already filled but not sealed yet. I have this block and I do a bunch of things to do register args. So basically create a new block. This will be something like let block prime equals the block modified, like something like this. And recreate a new block that is a transform version of this. Then, and for each of them, okay, I'm gonna write it in pseudocode in a comment just so that I have the logic here. For each incomplete, incomplete is not the right word. It's the word that the paper uses, but I don't like it at all in this context. Potential argument look up argument value in each parent. Oh, that means I don't actually need to know all the parents ahead of time. I don't need to know all the parents ahead of time, I suppose. Nah, I think it's fine to know them ahead of time. The problem is having them sealed ahead of time. Okay. Look at the argument value in each parent, which is fine because all of them are sealed if I'm sealing this. Update terminator instruction in parent. So register as block argument for each parent. Update terminator with argument. Unless all values are the same. If all argument values are the same, which we can't know yet at this point. I cannot know that. So, block argument for each parent, update terminator with argument. Register argument value. If all argument values are the same, revert parent terminator changes. Like, do not commit those changes, basically. Transform instructions to replace all instances of the argument with the unique value. Add the block to the list of sealed. Oh, that's not worrying about this. Okay. So that's what we do if there's a block that has already been filled that we try to seal. And then we can seal it, we can label it as sealed. Okay, so that's pseudocode to be written later. This is so that I remember what I have to do. And now, filling a block is filling a block is going over the instructions one by one. Okay. So, can I create a block? Yeah, I suppose if it is filled, I can create a block. If it is not, no, I can always create a block. It will just be incorrect in the worst case. Okay, so when we reach the end of a list of instructions, I return a block with the current set of instructions. and no arguments. No arguments if it is not sealed, and a panic terminator if I am in this case. Okay, so back to my state. The registers are for a given block, for a given name, what register that value is. It doesn't need to be a hash map per block, it's fine like this. The incomplete are, I probably want there to have a level of indirection because I will want to remove all of the keys. So here this will be so potential is what I've named it. Potential is for a given block, for a given role, for each parent. Well, if it's incomplete, wait, the incomplete ones don't need to know that information. Yeah, the incomplete ones are just a register. It's just a name. I don't need to do anything else, I think. Yeah, this is just, there is going to be a fee variable there. We don't need to know, we don't know what it is yet. So this is just for each block. This is the list of roles that we could not find locally that we will need to look up later. So this is hash set of role to be looked up later because they were not defined as part of this thing. So that's the potential. Yeah, potential. There might be arguments. Now the current, I think I'm going to introduce something else here. So sealed and blocks, this is fine. Those can remain. So have this empty hash map. Sealed blocks are those. I think for the current, I need to keep track of more things. I need to keep track of the list of instructions. Do I need to? Can I do a folder recursive thing that gives me the list? Like basically translates everything, and now it is a melodic operation at every step. I need to keep track. I might not need to. No, I don't need to. Okay. Current is fine. Current is enough. Okay. Okay, okay, okay. Whew. This is tricky. Which means regardless at the end of a fill block, I will obtain the block in question. So block will be the result of doing this recursion, I suppose. And I will need to modify the state of the blocks by doing an insert of the label and the resulting block. Okay? So lower function will be sealed block, filled block, and this returns a function. So it will need to do something, pure function something something. What is a function? It is a start block, a hash map of blocks, and the arguments to the function. Why do I need the arguments to the function? I don't need that yet. I will only need that. This kind of information is only important if I'm trying to generate another kind of IR, which is like the LLVM one, for instance, for where I actually declare proper functions with labels and stuff. I think, as far as I'm concerned, I don't really need that yet. And when I need to, I might just use. Yeah, I think I don't need that. And the start label is always the same. So maybe a function is just a hash map of label to block. Which I could replace by like a vector indexed at some point for efficiency. Okay. Start label for every function is always the label 0. Okay. I'm gonna need a few more things. I'll change those two other ones that are not accessed by anything else. So I can just give that. Why do I have sealed twice? Registers parents potential sealed. Those blocks here. And current. Okay. I might not even need current, come to think of it. Why do I need current? I need current because I will need to do lookups for the registers of like, hey, in this current block I'm defining, have I found anything? However, I can pass that as an argument to like, what is the thing I'm currently doing? Yeah, I don't need current. I don't need current. And I can probably remove this nonsense. Can I? Kind of want to guarantee that any lookup into this will succeed. No, actually, I think I'm gonna leave this. And since parents will probably... Nah, yeah, I'm gonna leave this. It's fine. Or maybe no, actually. Maybe no. I am going to do this. And I don't need the start label anymore. I don't need the start label anymore. Perfect. Both 0. Perfect. Registers parents potential sealed blocks. versus parent. Potential sealed blocks. There we go. Okay. Now, the top level thing becomes not use ls current, but make label with no parent. There we go. Seal block, fill block, purely return a and return a function, which is the result of applying the function constructor on a lookup of all of the blocks of the hash map of blocks. I guess I still need, no, to be, okay. To be clean, I will put the first label here, even though it will always be the start label. If I put this here, I don't have to make that assumption. I can always do that one. So let's go back to that. I would probably want to add, I haven't added the lens generation there. Let's do that quickly. Prisms of label, I don't need to, I think, but type terminator and target instruction. Type make prisms terminator. Come on. Target and instruction. Okay. Back to lowering. So we get the label and function start label. There we go. Seal block, fill block. There we go. Okay, that function should be done. This has a gigantic block of stuff not implemented yet, but with the logic of what we need to implement written down. Now, let's start to go writing the fill block function. So, current no longer exists. It's fine. So we obtain the block by going recursively with the go function. Okay. Which will give us a block as a result. I probably want to modify the block as I'm... Yeah, at the moment it means I'm going to add the instructions at the end with the list is absolutely ugly, but that way it means I have the tail call optimization kicking in. So, like, go, the current state of the block will be a block with no arguments, no instructions, and panic as a terminator. And we go over the instructions. This will give us the final block. We insert the block and we are done. Okay. So now, if we encounter, so our go function takes the current block and the list of instructions. If it's empty, we just return the block. That's basically, it's not exactly a fold because we are not going to want to iterate over the entire list of instructions all the time. But that's basically it. Like, okay, we've reached the end. The parent will have to deal. I think we probably want to return the block so that the parents. That means we probably don't want to insert the block in the map just because the parent might have to do some alterations. The parent can do the alterations on the hash map, I guess, rather than having to do. Yeah, okay, it's fine. Okay. Otherwise, if I have some kind of instruction I and a bunch of instructions IS, then it depends. Well, statements, I suppose. It's fine. This will be. Let's be explicit. This will be one statement from our AST. And here we have to decide, does that become a bunch of instructions within the current block? Or does that become a branching point? And therefore, I insert a new terminator into the current block. I'm thinking, sorry. Maybe I don't need to do this with the block. I can just do it by giving the full arguments that avoids creating unnecessary values. So this is args instructions terminator. And if we encounter this, we return a block which has the args, the instructions, the terminator. And in the case of we have the arguments, the instructions, the terminator, we look at the statement and we decide what we do. I was thinking of like expressions are going to be complicated to translate because this is where most of the lookups of variables is going to happen and the registering of registers. Can I do something else? Can I do break and continue statements? No, I cannot. I will need to, when I start processing the block of a loop, carry something in my state, which is where does a break go? Where does a continue go, basically? What are the targets of those labels? Okay. Oh, will I need to... I need to register the parent. So here basically is where... No, I guess the parents will always be registered ahead of time. Oh, but I don't want to register the parents ahead of time because I don't want to register the parents ahead of time because I might, because part of the process of filling the blocks is discovering where the outbound edge is, and if I don't fill it up ahead of time, then I don't have the problem of having to prune the edges afterwards. Okay, so go back to Monad. Make label does not require giving a list of parents. The list of parents is created as empty. And it is just fine like that. Which means here at the end, the outbound edge of this, where do we go from this thing? I need to do a case of the block terminator of the block I have just created of panic, nothing to do. Return, nothing to do. There is no other block that needs to go from this one. Jump to a label. I will need what is a target. Okay. I will need to register that in the parents, the hash map of parents needs to be modified with the concatenation operator, or insert with, the key is this next thing, and the parent is this current. I'm gonna rename it here as current. So since if my block ended in a unconditional jump, then this next block is added. Its parent will be this block I just came from. Actually, I'm just going to do it differently. I'm going to name those things to avoid having this nonsense. So target will have there we go. And I will need to add make lenses for target. here target, I can say that this is the target label, or perhaps even target. Okay. And branch is the last one I need to handle. This one, okay, so that's... And here I insert both as... So if I have an if block, it can go to two different blocks afterwards, either the if case or the else case, basically. So the parents of the if case now contains this block. And the parents of the else case contain this block. Okay. And since I don't have to dynamically decide the seal order, this is fine. Okay. Now, as previously mentioned, I need to go back to, oops, this is supposed to be the prompt. I need to go back to the monad, because I will need to keep track of, if I'm in a loop, what is the label I'm targeting as the output, what is the label I'm targeting as the condition. So that is maybe label, and let's break maybe label. Those are initialized at nothing. And I will probably want to use some kind of bracket notation to guarantee that I don't have to do the state manipulation manually to avoid a case of a continue and label being propagated beyond the scope where they're required. Okay. So if, let's start with the easy ones. What happens if I find a continue statement as part of the instructions of the current block? That's an easy one. What I do in this case is the current block ends. There are no more instructions after this. So, like, any instructions past this point is moot. The current block will not proceed beyond that. So, when null statement, when not null statements, I will do a emit a diagnosis of unreachable code. Whatever comes next is unreachable. So like you do a continue and you do a print the line afterwards, I can say like, hey, unreachable code there. And I'm just not even gonna attempt to translate it. So this, for now, I don't have any diagnosis emitting capability here, but emit diagnosis unreachable code. Then I know that the block ends here. So I can return a block with the arguments, with the instructions, and a custom terminator at the end, which is an unconditional jump. Oops, I'm just gonna answer this message. Okay, sorry about that. So here we know that in the case of a continuous statement, we cannot, the rest of the instructions are lost. We'll have to emit a diagnosis. And we know that this block ends in an unconditional terminator, which is just a terminator, which is an unconditional jump back to where the continuous statement goes. Those are not labels, they are targets. I suppose since I am inserting, by definition, the successor hasn't been filled yet, I don't have to worry about the arguments just yet. So, yeah, this is enough. So I can get the target is gonna be use of ls continue and on nothing m, as in I am encountered a continuous statement. Where does it go? It doesn't go anywhere because we're not in a loop or something is wrong. That's an internal compiler error. That's a bug on our end, not on the user's end, because we have already checked that all continue and break statements happen in a loop. So continue statement not in a loop. That's an internal compiler error. So now we get the target, and this is a jump to a target, which is this label, actually label, which for now, no arguments, because arguments will be added at time of sealing, which, oh, not necessarily actually, but they will be added either at time of sealing or at time of filling, and I know that the target has not been done yet by definition. Okay. Okay. So that's a continue statement. A break statement is gonna be basically the same thing. If there are more statements afterwards after a break, there are unreachable code, emit some kind of diagnosis, a warning, not an error. It's fine to have unreachable code. It's not an error. Just like emit a warning for the user, basically. Like, hey, that thing can't be reached. Just like, not even gonna try to emit code for it. And I try to retrieve the break target of the current loop. What label are we jumping to? If there is no such thing as no current state, that's an internal compiler error, and we can just panic. It's not supposed to happen. That means there's a bug in our code that's just like unrecoverable. And we create the result of this processing, which is a block with those arguments, those instructions, and a terminator, which is a jump to target label with no arguments. Those were the easy ones. Now, now, which one do I want to do next? Let might be the easiest. Because, yeah, anyway, all of those that require expressions are going to be a nightmare anyway, because I will need to do the expression thing. So, yes, for now, I'm going to assume the existence of a processing of expressions. So if I have a return statement with a typed expression, then what do I do on a return? First, I lower the expression. This is going to need to know about the current label, which is a thing I have not put in the state on purpose. I guess it could be there, but it's fine. It's not fine not to do it like this. So here, lower this expression in the current context. Do I want to put the arguments and the instructions in the state? I kind of don't want to. I kind of don't want to, because it means having to. The upside of putting them in the state is I don't have to thread them throughout all of the functions that deal with a given block. The downside is I have a lot of stuff that is only used for a block in the state that needs to be reset between blocks. Basically, every time I start processing a block, I need to make sure that I start with. That's not the end of the world. Yeah, maybe I put it in the state. Ideally, I'd have two separate states. I'd have the Okay, this is what I need to do. Okay, I'm gonna do that, and then I'll stop for the evening, I think, because it's getting late and I've been at this for a while. This is what I need to do. Okay. So, rather than current and everything, I am gonna introduce current, which will not be exported out of this. So this is parent potential sealed blocks, which will not be exported as part out of this. And current will be a current block state. And current does it. The problem is that a state needs to have an initial state, which means the current block state needs to exist. Do I just create a bogus current block state? Yeah, it's probably fine. It's probably fine. Or do I just set it to maybe and then. Do I set it to maybe and then all of my extraction functions? All of my extraction functions do the check that it's not empty, basically, and panic in case it is. It's probably better than having an undefined value. Yeah, okay, I'll do that. So this is a maybe current block state, which is set to nothing. What is a current block state? It is the label of the current block. It is the instructions of the current block, which for now are going to be a list, which is horrible, but it's fine. It's going to be a list of arguments, which are going to be a list of register, which is basically what is required to create the block at the end. And it is where does continue go? Maybe label. Where does break go for this block? Maybe label. Okay. And now what I'm gonna need to do is ideally I'd use the type system to prevent doing things not in oh, I could do something like this. Basically, what I want to do is a run block function that takes whatever is required for this block and will return basically will return the block at the end and therefore will always run with the current set properly. And what I'm tempted to do is I don't want to stack more monads on top of this, but maybe I could, is the thing. And that would remove the maybe. Yes, I think this is the way. So, the lowering monad is this nonsense. And what operations do I have in it? So I'm gonna need to do, okay, I'm gonna start doing a few more complicated things. So this is my lowering monad. This is what it is. I have a read access with a reader to an interface, and I have a state, which is this lowering state, which will be modified across the thing. I am gonna introduce a new type, block m, which is gonna be another monad on top, which is for the current block, which is gonna be a state t of the current block state on top of a lowering m. Which is going to derive all of the usual functor applicative monad. But it's also gonna derive monad fix and monad reader interface. So I still have access to the reader interface there. Actually, this is the wrong syntax. This is a block m of run block m of this. Something like that. So it still has access to the reader interface from the thing below. And crucially, it is still a monad state. It is still a monad state for the lowering state where get is lift get, put is lift put. We probably want. It's not monad trans no because it doesn't have an argument for it. Okay. And now the thing is, I can't make it. I can't make it a monad state for more than one thing. I think. I think the monad state constraint implies that the given monad has only one given state. Okay. So that means I can't use lenses. I can't use the same things they've been using otherwise for this thing. But it's fine because most of them will be read only anyway. Okay. So this, can I make it monad state lowering state without having to do that? Probably. That's fine. Go run read.t interface eval state initial state. Perfect. And the block monad is something else, and run block maybe I want to have the states first. There we go. And initial state is this thing, which doesn't need to be. There we go. Okay. And then we have the block monad that has its own state. And it has run block, which requires the label for the continue, the label for the break, an action in the block monad, and return something in the lowering monad. by having an additional state on top. So that would be label continue break. And what do I do with this? And some action. And a block of that action. I don't need to actually name it, and I'm going to name it. The run block is not required because it's completely internal to this thing. And this will be action and flip eval state, where the state will be the initial state of that thing, and the initial state will be this current block state, maybe just block state, which makes for a prefix BS. That's perfect. It's completely appropriate to what I'm doing at the moment. And this initial block state will be the BS label, which is the label, the BS instructions, which is going to be an empty list, the BS arguments, which is going to be an empty list. For performance, this would absolutely need to not be a list. But for now, it's good enough because we're going to be only appending at the end of a linked list. So it's going to be horrible performance-wise. This should be some kind of like sequence or like vector, even ideally, if we can like know ahead of time how many instructions we're going to need roughly. So, but for now, I'm using list. I'll do performance later. I want to make it work. And the upside of list is it is simple. And I just need continue, which is going to be continue. And I need break, which is the break argument. There we go. Which I guess I could rewrite as just eval state action initial state. Oops, nope. I'm just going to do generic. Oop, there we go. Need for a flip. All good. Okay. So now that means that state only exists when I'm within the block, which is nice. And that means I need to rewrite those things as being, I'm going to add an alias for lowering monad, which is, sorry, monad lowering, which is going to be a set of constraints that I require to be able to perform some of the lowering operation. And that state is monad reader interface and monad state lowering state, which is already provided by the block monad. That means that make label no longer needs to be in lowering. It can be in any monad that provides this, like the block M on top of it. So in the case of a monad lowering M, this can provide a label in that monad, whether I am in lowering M directly or something stacked on top of it. And likewise here. Okay. Let's do that here. And now what I want to do is with the current block state, current label will be something in my block M, which will give me the label. And current label is going to be so the problem is I am not in the case of a state monad because I am in something that wraps a state monad. So I might have to do a block M of do use BS label. There we go. Something like this. Just block M use BS label. Current. Okay. Continue label is going to be the same thing, but using BS continue. Same for break label. Things that are only read-only within the block. So I don't need to provide a lens. I can just do that. And I will need I don't need to read access to the instruction. I don't need read access to the argument. I can do append instruction that given an instruction perform an action in my block monad, and that instruction an action in the block monad, and that will be given some instruction perform something which is BS instruction will be modified by by appending a new instruction at the end. This is appending at the end of the list. That's why it's absolutely horrible, and why we will want to not use a linked list when we actually do some performance basic optimizing at some point. And append argument, it's going to be the same thing except it's a register. And this is going to be added to, so it should be instructions plural. So here instructions plural. And so here instructions plural, and here arguments plural. Okay. And now, armed with this, I can go back to here and this run lowering remains correct, but fill block is the one that is going to be running run block M. And so here I will need which order are they in here? They are in as continue break. So this is going to be the same thing. Run block M of current continue break. And now this is all within the block monad that we have added on top of our lowering monad. All of the state operations will still be performed on the underlying lowering state. And the only things that require being done are going to be done here. This is going to be, so the Go no longer has any of this. There might even be a better way of That's fine. Or like avoiding having to do the recursion manually, basically. That's probably a better way of doing this. Control monad loops. I can probably do that. I can probably use some kind of iterate until, where each step returns the next instruction to process. Just, okay, here's the next instructions, and when it's empty, but that means I need to. Or I guess until just might be the best solution, but that means I need to keep track of the instructions. Maybe I want some kind of like unfold R M or something like this. I want to keep. I want the state to be passed around to be some. Could be the list of instructions to process, basically. So that every step says back like, oh, here's the next instruction, and when it's done, it's done. Yeah, I think either I have to store the list of instructions within the thing, which I don't want to do, or I need to store or I need to store the yeah, okay. That's gonna be either way is gonna be ugly. I don't want to do either. So we're not gonna do either. So instead, the argument to go is the instructions. And I suppose no, I suppose I could register the Terminator in the state. But that's ugly. Okay, no, okay, so I will have to do the Terminator will be the result of processing the instructions. And the block will be make block of the Terminator. And make block of the Terminator will be something in the block monad that, given a Terminator, makes the block. And this is gonna be a lift A3 or something of the block constructor. Yep. And the three arguments, the three monadic arguments are gonna be current. I was gonna say it's gonna be a block M of lift A3 block of use the current instructions. I think it's instructions first. No, arguments first. So use the arguments. Use the instructions. And pure of the terminator. Okay. Which means now here that's just so I get the terminator and then I can create the block using that. So I guess I could even block is make block of go instructions. There we go. So here, if I find an empty list, then I return panic. Because unless the parent is able to determine that it is fine, like the parent will have to decide where we're going if there was no explicit thing. Oh, I guess I don't need to do that anymore. I don't need to do that anymore. Because the caller will always know what the context of the fill block is and can always say, this is what happens if there is nothing at the end. And there will be three possibilities. 4 possibilities. 5 possibilities? There is, we are in a loop. Therefore, if we reach the end of the instructions without encountering a terminator, we jump back to the given label, which is the loop condition. We are in an if block. If there's nothing at the end, we jump to the end of the if else block. We're in the else block. If there are no explicit, actually, there can't be anything. A continuous break. Well, if there's no continuous break that breaks us in the current loop, then there can be blocks within blocks. Is all of that nonsense because I will need to stack blocks? No. But maybe the current and maybe the continue and break will need to be persisted across different things. Yes, I think continue and break cannot work like this. The current block is definitely like each block is handled individually, but I need to be able to know when running a block if I am within the loop. And Yes. I will be stacking the calls to the block lowering function. I'm not gonna register the blocks ahead of time and call lower on top of them, which means each block will, when treating its successor, be stacking the context on top, I suppose? That's not true, actually. Let me think. That's not true. I would need to. I can finish the block and then go to the next one. Okay. I'm gonna stop here for the evening, despite the fact that I'm stopping in the middle of something. I need to figure out how I'm dealing with blocks like this so that I can figure out how I store the continue and break information so that if this, like, there is a block here that like starts making a graph like this, those need to know where continue and break go, so there needs to be some kind of stack of blocks I'm dealing with, and I need to figure that out. So I think I'm gonna stop here for the evening, and I'll resume on Thursday after having given some thought to how I want to do this, and I might change my current block M approach to something simpler if we end up having to stack. We will see. Or maybe. Yeah, okay. I'll think about it. I'll reach a decision before Thursday, or maybe tomorrow, depending on whether tomorrow I want to do an extra stream, because I really want to make progress on this and it's fun to do. But yeah, for next time, I'll give a thought about how I want to do this so that I can sort out this mess I've been making here and resume doing all of this nonsense. In the meantime, thank you for tuning in. I hope this was interesting, and I'll see you all next time. Oh, and I always forget to mention, but there is a Discord on the declarative.tv site with like a bunch of us who do stuff in Haskell and other declarative languages. So if you're interested in seeing other people who do the same kind of stuff, there you go. Anyway, see you all later.